Okay, so where we left off in the last video is we introduced Taylor's inequality. And the point of Taylor's inequality is that it puts a bound, an upper bound, on the absolute value of our remainder term. And remember, the reason we're concerned with the remainder term is if we can show that the remainder term goes to 0 as n goes to infinity, then that's how we show that a function is equal to its Taylor series centered at whatever number a we're using. But if this upper bound will go to 0 as n goes to infinity, then that's going to force this remainder term to also go to 0 because its absolute value has to be less than this thing for all of those values of x in that interval. So to prove this thing, first of all, notice that we're saying that this is true for all values of n. And remember, n represents the degree of our Taylor polynomial. Now for our proof here, we're not going to show that it's true for every single value of n. Basically, what we're going to do is show that it's show that it's true for n equals 1, and then sort of say like you can repeat the process that we're following in this proof however many times you need to show that the inequality is true for whatever value of n you're talking about. So that'll make more sense as we get to the end. Our goal here is to first prove that this inequality is true for n equals 1. Okay, so notice n shows up in a couple of places in this inequality. It shows up as the subscript of a remainder term, but then where it actually shows up in the upper bound, it's here and here. So both of these pieces of this upper bound are n plus 1. So when we're setting n equal to 1, then these two values are actually 2 because it's 1 plus 1 in each of these cases. So notice now in Taylor's inequality there's some assumptions. There's an if being stated here. If the n plus 1th derivative of f of x has an absolute value that's less than or equal to some number m on this interval. So whenever you see in a theorem an if statement, that's an assumption that you're going to make so that you can use that assumption in your proof. So in our case, when n is equal to 1, this would be the second derivative. F double prime of x in absolute value, we're going to assume is less than or equal to some positive number m, capital M. Okay? Now, in particular, f double prime of x, even without the absolute value, would have to be less than or equal to m because otherwise this wouldn't be true. So what that means is on this interval right here, if x is between a and a plus d, which remember, we're talking about this interval right here, a would be right in the center of that interval. So what I'm doing right here is I'm choosing values of x that are in the right half of that interval right there. We could say that this is true. The integral from a to x of f double prime of t dt is less than or equal to the integral from a to x of capital M dt. Same limits of integration. Because f double prime of t is less than or equal to m, we have this property of definite integrals that we talk about in Calculus 1. So this would be true. And the reason we needed to assume that x was in this half of our interval is because we want x to be greater than a, so that this is a lower limit and an upper limit that's actually greater than our lower limit. Otherwise, that can mess with this inequality. All right, now if we actually try and evaluate these, the antiderivative of f double prime would just be f prime, or an antiderivative, but that's the one that we're going to use. So when I evaluate this, I'm going to get f double prime turning into f prime, and I evaluated x and at a, and I subtract those because that's how we deal with definite integrals. So this definite integral on the left-hand side works out to f prime of x minus f prime of a. On the right-hand side, I'm integrating a constant. So the antiderivative here would be m times t, and I evaluate that from a to x. That's going to look like this. Capital M times x minus a in parentheses. Okay, so because this inequality held here, and this is what these two definite integrals are equal to, then I still have that inequality here. I can add that f prime of a over to the right-hand side and get this. F prime of x is less than or equal to f prime of a plus capital M times x minus a. Okay, now what I'm going to do is take that inequality and I'm going to integrate both sides a second time. Okay, and I'm going to integrate it over the same limits of integration, so from a to x. Because the inequality held for these two integrands, reusing that property of definite integrals would say that this definite integral has to also be less than or equal to this definite integral. But kind of repeating that process, if I were to integrate f prime, I know that an antiderivative for that is just f of x. So evaluating that from a to x, I get f of x minus f of a. That's what this definite integral works out to. Over here, f prime of a is just a constant because we're plugging a number into it, a. So integrating that is going to give me that same constant times the difference between these limits of integration, x minus a. Here, I had to replace the x on the previous page with a t because my x is being used here now, so I'm using a dummy variable. We've done this before. But when I integrate this, now I have the variable t appearing in this expression. It's just a linear function of t. And so integrating it will give me a quadratic function, x minus, or it's really t minus a squared over 2. But then I evaluate that from x to a. So when I plug an x in, I get this. If I plug an a in, I would get a minus a, which is 0. So that's why I don't see a minus m times a minus a squared over 2 over here. It's just 0, so that goes away. Okay. Now what I can do is I can take this term here, subtract it over to this side, which gives me f of x minus f of a minus this thing, f prime of a times x minus a, which is less than m over 2 times x minus a squared. Okay, but think about what the remainder term would look like. By definition, remember, we're assuming n is equal to 1 here, so we're talking about the first degree Taylor polynomial and its remainder. R1 would be equal to f of x minus that first degree Taylor polynomial. That's the definition of that remainder term. But that first degree Taylor polynomial would look like f of a plus f prime of a times x minus a. Those are the first two terms in our Taylor series, which means that makes the first degree Taylor polynomial. Of course, since I'm subtracting it, I have minuses in front of those two terms. Okay, so here I have that r1 of x is equal to this, but this exact expression is what's showing up here, which we already showed was less than or equal to m over 2 times x minus a. So that means that our remainder term, r1 of x, is less than or equal to m over 2 times x minus a squared. Okay. Now we can make a similar argument using the fact that f double prime of x would also have to be greater than or equal to negative m. And again, where that's coming from is from our initial assumption right here. So remember, you can turn this thing into an inequality this way, like that. So previously, right here, I used this part of that compound inequality, but then I could go an additional step and use this part of the inequality, which is what's being stated right here. And you could go through a similar argument to show that r1 of x is greater or equal to negative m over 2 times x minus a squared. Because it's so similar to what we already did, we're not going to walk through all those steps. It's not really worth the time. But if you take these two inequalities together, we can consider that like a compound inequality, which can be rewritten in absolute value form this way. The absolute value of r1 of x is less than or equal to this expression right here. So this is exactly what Taylor's inequality would look like in the case that n is equal to 1. I'd have m over 2 factorial, which is just 2, times the absolute value of x minus a squared. Notice that's what we ended up with right here. So what that does is that confirms Taylor's inequality for when n is equal to 1. What you can do is, there's a little sentence right here kind of indicating that if you wanted to prove the case where n is equal to 2, you just have to go through that argument. Notice that argument required us to integrate our function a couple of times. In the case of n equals 2, I would have one additional integration step to show, but the argument would look essentially the same. So noticing that pattern, we could say that this could be repeated any number of times to show that it's equal or that the inequality is true for any value of n that we wanted to use. So now we return to this. We already showed what the Taylor series or the Maclaurin series for e to the x is, but what we have not shown is that e to the x actually equals its Maclaurin series. So to do that, we need to show that the remainder term for the Maclaurin series for this function goes to 0 as n goes to infinity. Okay, and the trick is going to be to use Taylor's inequality. So let's return to Taylor's inequality for a second and see what it is that we actually need. So looking here, if the n plus 1th derivative of f of x has an absolute value that's less than or equal to m for this interval. So I'm going to stop there. What we need to do is identify some constant that this holds on, or some constant that we can use for this inequality on some interval here. Okay, so remember that we're talking about a Maclaurin series where a is equal to 0. So when we talk about x minus a being less than some number d, so I'm going to say assume for some number d, okay? In other words, the absolute value of x is less than d. So I'm letting d be any real number, but I have to say that d is some real number to be able to use an inequality here. We're going to assume that the absolute value of x is less than d, so that x is in the interval negative d. Remember, that interval is what this inequality represents, okay? So what I need to do now is look at the n plus 1th derivative. The absolute value of f, the n plus 1th derivative of f of x. Because we're talking about the exponential function, the absolute value of the n plus 1th derivative of f of x is the same thing as the absolute value of just e to the x, because every derivative of e to the x is e to the x. Now, what I'm trying to do is find an upper bound for this inequality. If e to the x, if I was just considering the entire function on the entire domain, then there is no upper bound for that because e to the x goes to infinity as x goes to infinity. But we're assuming that x is restricted to an interval. And I know that e to the x is an increasing function, so that as x gets bigger, the exponential function gets bigger. And also, the exponential function is always positive anyways, so the absolute value here doesn't really make any difference. But if x belongs to this interval, then d is larger than any value of x I can choose from here, which means e to the power of d is going to be larger than e to the power of x. So that this thing right here is filling the requirement of that capital M that's showing up in Taylor's inequality. That thing is like the M in Taylor's inequality, okay? So now, by Taylor's inequality, so coming back over here, Taylor's inequality says that the absolute value of my remainder term is less than or equal to this expression here. So the absolute value of Rn of x is less than or equal to capital M, which we found is going to be e to the power of d, over n plus 1 factorial, times, and again over here, x minus a to the power of n plus 1, except x minus a in this case is just x. Remember, a is equal to 0. So this is the absolute value of x to the n plus 1th power, okay? Now, keeping in mind, let's go like this. The absolute value of x plus, or the absolute value of x by assumption is less than d. So this expression is less than e to the d over n plus 1 factorial times d to the n plus 1th power, because of that assumption that we made, okay? I'm going to write this in a slightly different form. I'm going to take the e to the d out front, and I'm going to put the d n plus 1 over n plus 1 factorial right there. All right, now remember what the goal is. I want to show that as n goes to infinity, my remainder term goes to 0. If the absolute value of my remainder term goes to 0, then the remainder term also goes to 0. But this is an upper bound for that remainder term on the interval that we've specified here. So if I can show that this goes to 0 as n goes to infinity, then the fact that this has to remain less than or equal to this would imply that this also goes to 0. So now we're going to look at the limit as n goes to infinity of this thing right here. Limit as n goes to infinity of e to the d times d to the n plus 1th power over n plus 1 factorial. Okay, now notice I could pull that e to the d out. Okay, notice also, limit. I can pull the e to the d out because there's no n in there, so it doesn't depend on this n in my inequality right here. Notice also that as n goes to infinity, n plus 1 also goes to infinity. So I can swap these n plus 1s out for n's if I want to, because in either case, this exponent and this this factorial are going to infinity. So I can also write this as d to the n plus 1 to the nth power over n factorial. It's the same thing, right? Does this go to 0? Well, this actually looks kind of familiar, because if you recall, we found the Maclaurin series for e to the x already. We found it right over here. And if you notice, its terms have the form x to the n over n factorial. We also know that the radius of convergence of this power series is infinity, which means this thing converges for every value of x that I can plug in here, including d, whatever d happens to be. But the fact that this series converges means that its sequence of terms has to go to 0. Remember, that's our divergence test from way back earlier in this chapter. So using that, we know that this limit has to go to 0. Otherwise, that power series for e to the x wouldn't converge on an infinite radius of convergence. So this has to go to 0. So by that inequality, the remainder term has an absolute value that goes to 0 as n goes to infinity, so that e to the x equals its Maclaurin series. Okay? Now notice, again, sometimes students will get hung up on the fact that we introduced some number d here without ever specifying what it is, and get hung up on the fact that, well, we only showed that it converges on this interval. But notice, no part of our work here depended on what d was actually equal to. This result here is going to be true regardless of what we're plugging in for the d. So that's important, because I can make this interval as big as I want it to be, and I still get the same result. That means e to the x equals its Maclaurin series for all values of x. Okay? All right. So we have one Maclaurin series down for the exponential function, and now we want to find some more Maclaurin series for some familiar functions. We're going to look at sine of x, and we're going to look at cosine of x. I want to find the Maclaurin series for f of x equals sine of x, and then show that it's equal to f for all values of x, just like how we did for the exponential function. So remember, the first goal is to find a bunch of derivatives for your function. We have f of x equals sine of x by definition, so that f prime of x would be cosine of x. F double prime would equal negative sine of x. F triple prime is equal to negative cosine of x. And then as soon as I get to my fourth derivative of x, I see that I'm right back to sine of x, which is where I started from. And this is typically what you're doing when you're trying to find a Maclaurin series or just a general Taylor series centered at some number a for a function. You want to find enough of its derivatives until you see some kind of pattern emerging. And we already know this about the sine and the cosine function. When you keep taking derivatives, you get this pattern of the same four functions occurring in this sequence over and over again. It's a Maclaurin series, which means we want it centered at 0. So for each one of these, I'm going to be plugging 0 in. And this is going to be part of where I get my coefficients from. Okay? So sine of 0 is equal to 0. Cosine of 0 is equal to 1. Negative sine of 0 is 0. Negative cosine of 0 is negative 1. Sine of 0 is 0. So what I end up with is this alternating pattern. 0, 1, 0, negative 1. 0, 1, 0, negative 1. That's going to continue forever. So now if I want to write the Maclaurin series for this, I have f of x is equal to, well, my constant term would be 0, and then my x term would be 1. So that's x. Okay? My x squared term is going to be 0, so I'm not going to write it. But my x cubed term is going to have a negative 1 in the numerator over, remember at this stage we're looking at 3 factorial. It's the third derivative at 0 over 3 factorial, and this is now my x cubed term. My fourth derivative is going to be 0, and then if this pattern continued, my next derivative would give me a positive 1 at 0. So we have a pattern emerging. That would have been my fifth derivative, so that I get 1 over 5 factorial, and that's my x to the fifth term. And so if you notice what's happening is we're getting all of the odd degree terms out of this thing, and all of the even degree terms are going to 0. And then in addition to that, we're looking at an alternating pattern of negatives and minuses and pluses here. So I could predict what my next factor, or my next term is going to be. Negative 1 over 7 factorial x to the 7th, which is going to just continue indefinitely, with only those odd-powered terms appearing in this, this expression. So I could write that in summation notation this way. N equals 0 to infinity. Because I have an alternating series here, I'm going to want to include a negative 1 to the n. And remember, sometimes this has to be negative 1 to the n plus 1. But you just need to check it against your first term to make sure that it comes out to the right sign. So here my x does not have a minus in front of it. So I'm going to think of that coefficient there as being a positive 1. Negative 1 to the n, if n is equal to 0, would be a positive 1, so that does start me off where I want it to be. Negative 1 to the n. Now let's look at the x's and my denominators. The power on my x matches the thing I'm taking a factorial of in my denominator. 3 and 3, 5 and 5, 7 and 7. So whatever I put for my exponent on my x here, I want that to be the same thing I'm taking the factorial of down here. Now, because we're looking at odd numbers only, one way to get an odd number is 2n plus 1. If n is an integer, multiplying it by 2 would give me an even number, and then adding a 1 to that would give me an odd number. Does this give me the correct odd numbers? Well, starting when n is equal to 0, I'd have x to the first power. That works. N equals 1 would give me x to the third power. That would be my next term. So this 2n plus 1 appears to be doing what we want it to do. And like we said, that's the thing we're also taking the factorial of down here. So this is the Maclaurin series for the sine function. One thing that's important to note, which is a good way of remembering this Maclaurin series, especially when we talk about cosine, which looks kind of similar, we know that the sine function is an odd function. We also know that polynomials can only be odd functions if all of the exponents that appear in that polynomial are odd numbers. So that correlates here. Sine is an odd function, and if I think of this power series as an infinite degree polynomial, all of the exponents appearing in this power series are odd numbers, just as we would expect. Okay, so that's the first step. We found a Maclaurin series for sine. Now we want to show that the Maclaurin series is actually equal to the sine function. And we do this in a similar manner as what we did for e to the x previously. So again, we are looking at, we're going to look at Taylor's inequality. And as before, we're going to let the absolute value of x be less than some number d for some d. And I'm going to say positive d because it would have to be positive for this to be true. Okay. Now, remember, Taylor's inequality says that we're looking at some restriction or some upper bound on the absolute value of f of n plus 1, or sorry, the n plus 1th derivative of f of x. What's nice about this is that even though I do get different derivatives, it's not like e to the x where I keep getting the same thing each time. Even though I keep getting different derivatives in the cycle of 4 over here, all of them are plus or minus a sine or a cosine. And we know something about the sine and the cosine function. The absolute value of sine or cosine, or negative sine or negative cosine for that matter, is always less than or equal to 1. This is always true for the sine and cosine function for any value of x, even if we don't restrict x to an interval. So that 1 right there is going to fill the role of the m in Taylor's inequality. So now, by Taylor's inequality, we can say this: the absolute value of r to the n, or Rn of x, is less than or equal to capital M, which in this case is just 1, over n plus 1 factorial, times x minus a, but remember a is 0, so we just say the absolute value of x to the n plus 1th power. Okay, now here I can take that absolute value of x and say, well, that's just less than d because of this restriction here. And I can write that this is less than d to the n plus 1 over n plus 1 factorial. We already saw that this expression goes to 0 as n goes to infinity. So, or therefore, or thus, I can say that, sine of x is equal to its Maclaurin series. Okay, so we could do this for every single Maclaurin series that we come up with. We're only going to, in this lecture, we're only going to prove using Taylor's inequality the 2 examples we've already done. We will come up with Maclaurin series for more functions, but from here forward, we're just going to kind of state that they are equal to their Maclaurin series without going through this stuff here. You will have to do some of that in the homework. Let's pick this up again in the next video.